lecture 13. Moving back now from differential equations, which isn't my specialty, Laplace, heat equation, wave equation, back towards dealing with data, probably closer to problems that are central for the lab. Part of it's linear algebra, of course. Kalman filter and other estimation problems coming up. And by the way, on those, I'm not an expert. I'm going to be learning as fast as I can, and I will appreciate suggestions, advice, guidance on what would be most useful there. And then, of course, further in the future come signal processing, image processing, wavelet ideas. That's all coming. So today is this lecture is this fundamental problem of dealing with, of getting, of using orthogonal or orthonormal vectors. So I'm in finite dimensions mostly. Also, I better make a remark about how nice it is when functions are orthonormal too. But for the most part, vectors. And we've seen already the meaning of orthonormal, that their inner products are 1. That's the normalization, length 1. But the main point is, of course, that they're mutually orthogonal. And then the good way to express this fact is to put those Q's into a matrix. So I don't know if I've made that clear. The columns, here's my matrix Q. I've just put these in the vectors in the columns of the matrix. Here's my matrix Q transpose. The Q's are in the rows. And then I do the matrix multiplication. And the ith one against the jth one gives me a 0. A higher up ith one against a later jth one would give me a 0 there. And of course I get 1s on the identity when the row and column match. In other words, I'm getting the identity matrix. So this is the shorthand for and the neat fact that says I've got a matrix with orthonormal columns. That's a heck of a long expression, and I'm sorry we don't have a totally conventional word for that. Maybe I'll just call it orthogonal matrix. So Q transpose Q equal I. That's going to stay on the board, whatever else might disappear. Okay, now, so what are my thoughts for the lecture? First of all, to say, why is orthogonality good? What are the virtues of having an orthonormal basis? And I can only probably mention some of them, but it's certainly desirable. Then, how do you get it? If you have a basis of vectors that aren't orthogonal, how do you straighten them out to get right angles? So that's the orthogonalization. Another heck of a long word for the subject of the lecture. So the virtues of it, how to get there, and then, because there are several ways to do it, Gram-Schmidt, the most famous, but not the only, and then the costs. So I've listed here in this list, we know what orthogonal matrices are, so something about the virtues, something about getting there, something about the costs, and then some applications. Some of the applications of QR. Right. Okay. So I use the words QR there, which is the shorthand for this process of orthogonalization. Okay. Now, virtues first. Well, maybe one way to say, one virtue to point to is that when I multiply by an orthogonal matrix, I don't change the length of the vector. Let's just see that point. So crucial point is that what's the length of a vector? First, I have to say what's the length, and then we'll check that it doesn't change. So what's the length of a vector? I'm taking the ordinary Euclidean length, it's often called, or L2 it might be sometimes referred to, but that sounds a little exotic. It's just the sum of the squares. The sum of the squares, well, if I make it a square, then I don't have to take the square root. So it's the sum of the components squared. And it's also x transpose x. I mean, that's what x transpose x is, like a shorthand. The matrix multiplication does it for us. And of course, that's exactly what we did here when we took qi transpose qi and got 1. That was saying that the length was 1. Okay. Now, okay. Now here I claimed that if I multiply by q, I don't change that length. So how would I prove that? Let me square it again just to avoid having to write square roots. Why is it that the length of qx, I want to say that the length, that this is the same as that. And the reason I like that, the reason that's good is that it means vectors can't get out of control. Numerical stability is terrific if I'm working with orthogonal matrices. So that's one virtue, is the sort of numerical stability. There's the condition number, which I'll speak more about this afternoon. The condition number of an orthogonal matrix couldn't be better. It's 1. Those are the matrices that have condition number 1. And other matrices have higher condition numbers, so errors could blow up. And if we iterate, they could blow up a lot. But nothing can blow up with this. It's okay. Now, why is this? So the length of qx by this same formula should be qx transpose qx. We're just using the length formula for the vector qx now. Okay, so what do I do to make everything clear? Sort of multiply it out. So that's x transpose q transpose qx. And now the key step is I put the parentheses in a smart place. I mean, that's so many of the basic linear algebra arguments are simply do that multiplication first. Keep them in the right order, of course, but do the multiplication there in the middle first. And of course, that's the identity. So that's just x transpose x, which is x squared. So am I there? Okay. Oops. So lengths don't change. Also, angles don't change. We could check that too. That might be, maybe I'll try to include that in the notes, that the angle between two vectors doesn't change. If the vectors are, if two vectors are orthogonal and I do a q on both of them, they're still orthogonal. How do we actually think of, I mean, give me some examples of q's that, of orthogonal matrices. Let's take some examples. So we know this fact. So this might be a good spot to put in some examples. Give me a simple 2 by 2 example of an orthogonal matrix, or 2 by 2. So what's a typical orthogonal matrix that's 2 by 2? It's a rotation. Now that we know orthogonal matrices are the ones that don't change length, we can sort of think geometrically. What can we do to the plane that won't change the length of any vector? And one thing we can do is to rotate it. So the rotation matrix is cos theta, sine theta. That's a unit vector, of course, in the theta direction. And now I want the perpendicular to it, so that will be minus sine theta cos theta. That's a, you see that's orthogonal to that. They're unit vectors. We've got this is a rotation. This is a rotation, of course. Maybe I mention, two things come to mind. I could mention another unitary matrix, another rather simple one. But these are maybe the most basic building blocks. I guess it's probably true that if I take a 6 by 6 orthogonal matrix, say I just made up 6 by 6 orthogonal matrix, probably it can, I think that's true, it could be written as a product of these 2 by 2 rotations. Rotating in the 1, 2 position and the 1, 3 position and the 2, 3 positions. So all the I, so how many rotations are we likely to need? If it's 6 by 6, let's just figure it. 6 by 6, I'm figuring I can make it a product of things that are these plane rotations, say, and here's a rotation in the 2, 5 position. Can I just write C in row 2, S in row 5, minus S in row 2, C in row 5. That would be a 2, 5 that would be a rotation in the 2, 5 plane. And it seems reasonable that how many different planes are there? How many pairs, I guess, yeah. How many pairs are there? Yeah. Choose any of them. So let's see, I've got 6 choices for the first row to use and 5 choices, maybe 30. Maybe there are 30 rotations produce a more general orthogonal matrix. Probably it's almost every, let's see, the only thing I notice is that the determinant of that is +1. And if I changed a couple of signs, I could have made the determinant -1. So that's pretty minor difference. Anyway, numerically this is important too. We'll see that a way to construct a orthogonal matrix is by a product of these plane rotations. Okay. For 6 by 6, well, yeah, I think, well, let's see. Yeah, it's a good question. What can we achieve? Like, suppose we have this full 6 by 6 matrix. What can we achieve with 1 rotation? That's a good question, and it'll come up. So, like in the 1, 2 position. Say I do it in the 1, 2 up in this corner. What could I do to my orthogonal matrix suppose I multiply this orthogonal matrix, say it's 6 by 6, and so this is what's going to happen when I multiply. So this is really 6 by 6, but it's all the rest is zeros. Sorry, it's not very. It's meant to be up in the left corner of this 6 by 6, and here's my original one. What could I do? What could I achieve? It's like elimination, and probably, yeah, very like elimination. I can probably get a 0 in the answer in that 1, 2 position, for example. I think I could do this. So here's my orthogonal matrix, and I'm trying to simplify it. I'm trying to do elimination, but with these special rotations. And if I rotate in the 1, 2 plane, I think I could realign these things to get a 0 there. And we could figure out what theta would do the job. But I think, to follow up, I think I can probably only get 1 0 there. And then I'll need another guy to get another 0 somewhere else. And then I'll have to think, yeah, so then I keep getting a whole lot of guys that produce zeros, and in the end I have the identity matrix. So then all these little rotations are, well, I guess the inverse of that. And sorry, if I transpose them, I've got the thing itself. So are you kind of seeing this is what numerical linear algebra people like go to sleep thinking about. Can they do a bunch of rotations and reduce the matrix? Well, while I'm on that subject, they have what bothers them, what they lose sleep over is this, that suppose the next step would be to try to get a 0 there. So here's my usual, it's like elimination. I get a 0 there, can do. We could figure out what the angle should be, no problem. Then we go to get the next 0. So how are we going to get a 0 in the 3, 1 position? Well, we're going to do a rotation in the 3, 1. We're going to do a 3, 1, right? This will be a C minus S, S, C in the 1, 3, in rows and columns 1 and 3. But, do you see that? I haven't really given you much to look at here, but maybe you could guess what's going to happen. I do a rotation in the 1 and 3 position, so it changes rows 1 and 3 and columns 1 and 3. And what's the danger here? Can you anticipate what? Yeah? I'm going to mess it up. I don't want to mess it up, but it's certainly a danger that I will. Right. And actually, I should be, yeah. If you want to, right, yeah. So the danger is I mess it up. In fact, I will mess it up. Okay, so then you have to think, is there a way to do it so that you don't mess things up? And so I've got into this topic earlier than I intended to in the lecture, but just so you sort of see what enters in the linear algebra here. Well, suppose here's the trick, that I can do it without messing up if I'm not quite so ambitious. If I say, okay, I'll live with stuff. Also, I won't shoot for that to be 0. I'll start my zeros down lower, and just, do you see what's happening here? The claim is that I can get those zeros. So that's a matrix. Is that matrix upper triangular? No, I didn't get that far. If I could have got that far, that's more than man can do here. I've got to allow myself one diagonal below the diagonal. Then it's possible. So how would I get that 0? Let's see if we can imagine how to do it. I'll get that 0 by a 1-2 rotation. I can get that 0 by a 1-2 rotation because the 1-2 rotation alters column 1, and probably I can get it. Then I'll get this 0 by a 1-3 rotation. You see, I'm sort of chasing these non-zeros out of the matrix, but it's leaving me a little more. Okay, can I not go beyond that? But it's a highly important point. And if the same thing if I had a symmetric matrix. If I had a symmetric matrix, I might want to do these rotations and get zeros, but I would have to accept a diagonal below the main diagonal still non-zero. Yeah, right. Okay, so that's a point of interest. All right. let's see, I wanted to say one more thing about these rotations. And to connect them with, yeah, so here's my other point about rotations. Can a rotation be, yeah, here's this is like coming up quite a bit in applications. Can I write a rotation? So is it all right just to write CNS for cos theta and sine theta and minus sine theta and cos theta? Now, so here's like a separate question. Could I write it as a product of matrices of the kind we've sort of come to know and love? Something up here, 0 there, something there, 1, 1, 0, and something here, 1, 1, 0, and something here. And the answer is yes. That can be done. Let me see. I think I can tell you what those things are. I think it's cosine minus 1 over sine. And I think this one is sine. And I think this one is cosine minus 1 over sine. Now, what's good about this and what's a little unusual? What's good is that these three matrices are particularly simple to execute. What does that do? If I had a good picture I could show you. Suppose we have a picture here, an image, and we want to rotate it. So we want to multiply it by this rotation matrix. We want to multiply, we want to apply that rotation matrix to all the little pixels and turn the face. You can see computer graphics is going to want to do this. So the question is, can we do a rotation as a sequence of these guys? And this formula is saying yes, we can. Okay. Now, what kind of a matrix? What does this do to the plane? I said that this thing rotates the plane. We have a really good image of what that does. Now let me ask you, so I've lost orthogonality here, and that's part of the point. Suppose I have a matrix like that. What does that do to the plane? Do you think of a matrix as a transformation? It takes every vector in the plane and multiplies by the matrix, and so it moves all those vectors. Let's see, what will happen if the vector is, say, in the x direction? So if I start with a vector x is 1, 0, and let me call this S, for example. I'll call that matrix S. What is Sx? Is it still 1, 0? Yes, okay. So this is Sx. Didn't move, actually. So it's an eigenvector. Eigenvalue 1. Okay, let me take another guy, because if I take 2, I'll know everything, right? If I know what it does to 2 vectors, I know everything. Okay, what does it do to y equals 0, 1? Well, I multiply S by y, and what do I get? C1. So it goes there. Now, what kind of a, do you know the word for a transformation that, so what is it doing here? Let's see, I'm not, are you seeing what it does to the whole plane? Vectors that are in this direction stay put. Vectors that are here kind of shear over a little bit. All these vectors get tilted. Vectors here go, the word is a shear. What it does is like these matrices will, one of them will shear the thing. It's like it pushes this edge up, like so, somehow. And then the second one shears in the other direction, and my arc is going to let me down now. And the third one shears again, and the result is a rotation. I'm remembering vividly a visit, my only visit to National Institutes of Health. Well, it didn't have anything to do with medicine or anything, but there were a few mathematicians there I hadn't met and wanted to in Maryland. And they had just implemented this idea in a very elegant way, and were very excited about the stability and the efficiency of their rotation. Part of my point, I guess, is just that factoring matrices in interesting ways is pretty is a piece of applied math. And what's interesting a little about this factorization is, you see, we'll see this again in future things. These matrices are particularly simple. This involves sort of a butterfly as in the fast Fourier transform. You may have seen that butterfly picture because I have two inputs and two outputs. So the matrix for this, I have two inputs, then the C and S and minus S and C affect the two outputs, so then I get two outputs. So each output is involved with both inputs. What's happening here? I have input in the first coordinate, input in the second coordinate. Now, when I multiply by this guy, which was this sort of thing, the thing in the x coordinate didn't change. The thing in the y coordinate was affected by, you see what happened? The thing in the y coordinate was changed to C1. It was affected by the x coordinate. So it's like these involve like can I say a one-winged butterfly? And then the next step here will be this one now gets affected by this one. But this guy goes through. And then the last step will be this guy goes through, and this one is affected by this one. So we have produced a butterfly out of three one-winged butterflies. Oof, what a weird description. But there are simple ideas like that have applications that were kind of unexpectedly simple but important. And but there's a little bit of linear algebra here that I don't feel I have completely clear. We're factoring an orthogonal matrix, and these guys are simple, but they're certainly not orthogonal. So there's some linear algebra there of how if I start with an orthogonal matrix and I factor it into these elimination type matrices, we've lost orthogonality, but if we do it right, the product will come out orthogonal. Okay, that's I've really digressed now twice because of the simplicity of these 2x2 rotations, and this was a digression into what are called Euler angles when I'm creating a matrix operating on a matrix by these plane rotations, and this was a digression that we'll appreciate later. But it's sort of like simple enough to see it happen. Okay, can I come back to the main theme, which is right now the virtues of orthogonality. All right, let me do that. The virtues of orthogonality. Okay. Well, all right, take that guy out of it too. Okay. The virtues of orthogonality. All right. Suppose I have an orthogonal basis. I've got these guys. And I've got a vector which I would like to express as some combination of these orthogonal vectors. My question is, what is C1? If I have an orthogonal basis, one of its virtues is that if it's a basis, then any vector is a combination of those basis vectors. One of the virtues important virtue is that the coefficients, C1, C2, Cn, I can find quickly. And how do I do it? Can you take that inner product? Right. Take the inner product with, how will I find C1? Take the inner product with Q1, right? Then all this stuff will disappear. So Q1 transpose X, that's the inner product you wanted, is C1 times Q1 transpose Q1, which is 1. C1 times 1. And all that stuff is 0. So you see, we immediately get those coefficients. Can I write that in matrix language? You're going to see the same thing, but it's so important. And by the way, yeah, okay, let's just see the same thing in matrix language. Here I have a vector x, and when you see a combination of vectors, how do you see that in matrix language? I want to express it using the matrix Q, of course. The matrix Q is going to be always stand for my matrix with these Q's in its columns, Q2, Qn. Okay? And I've got coefficients C1, C2 up to Cn. What's that right-hand side in matrix language? QC, thanks, QC. It's Q times C. Because if I take Q and multiply by, now let me put in the C. If I multiply by C1, C2, down to Cn, this is exactly what that does. It takes C1 times Q1, C2 times Q2, Cn times Qn. So X is QC. All right, now what's C? If I have an equation X equal QC, what is the answer? What's the solution C? What are the coefficients? In matrix language, what do I do to this? What do I do to this equation to make it to produce C? Multiply by Q transpose. Thanks. Multiply by Q transpose, and I have Q transpose X equals C. And you see that that's exactly what we did here. The first C was the first row of Q transpose. If I write more C's all at once, you see that did it all at once. Here I'm doing them like one at a time. To get C2, I'm doing Q transpose, Q2 transpose X. For the same reason, that would give me C2. And that's just the second row of Q transpose X equals C2. Okay, so that's great. Now, actually, I'm ready to start. So these are like great advantages of having orthogonal bases. That lengths don't change, that I'm working with simple rotations, that I can do projections and I can do change of coordinates very quickly, always because of this formula, which is firmly on the board. Okay. Now, oh yeah, okay, let me ask you, let me go back to least squares. Let me go back to least squares. Well, I have to, I guess, yeah, let me go back to least squares. So here's a question. Okay, so remember how least squares started? We had a system AX equal B. which had too many equations, for the number of unknowns, so there wasn't a solution. And how did we get the solution? What was the best x? Everybody remembering that, the equation for the best x? The equation for the multiplied by A transpose, we took A transpose A for the best x was, A transpose B. Okay. This is the best x. Best meaning it makes the error as small as possible. Best x means we're minimizing the distance between ax and b, and that minimum is achieved at x hat. That's what best meant. Okay. Well, let's see if I can make my point here. Suppose we, this is the way it's usually done, solving those equations. But there's another way to do it. It would, I guess, here's the way to make my point. How simple this would be if A was Q. If A was Q, what would be the best choice? So let me just put over here. If A was Q, if A, should I say was or were? Was. Were is the subjunctive, right? If A were Q. In other words, if A had orthonormal columns and wasn't just some rectangular matrix, it was a rectangular matrix with orthogonal columns, then what would be the best x? Well, it'd be just Q transpose B, because this would be the identity, right? So the beauty, again, another way to say the beauty of orthogonality is it makes that matrix the identity, and then the best x becomes A transpose, well, it'd be Q transpose B. Actually, this is just the kind of thing we did here. Just the kind of thing we did here. We're trying to minimize this, and oh yeah, here's a quick way to see that. Well, okay. If A was Q, yeah, should we just like some practice? We're trying to minimize, if A were Q, we would be trying to minimize QX minus B. And the claim is that that's the winner. Now, I would like to see that really quickly. Suppose Q is one of my, Q will always stand for the matrix with Q transpose Q equal I. How can I see that the right thing to do, that this is the winning choice? It's a projection, that's true. That's a good way to see it geometrically. I was going to suggest also an algebraic way to see this. Suppose I multiply this thing by Q transpose. Suppose I multiply, this is the error, right? Suppose I multiply by Q transpose. Then what do I have when I multiply that thing by Q transpose? I have X minus Q transpose B. And what's the connection between that one and this one? They're the same. Why is that? Because I multiplied by a Q transpose, which is one of my orthogonal guys. Q transpose is yeah, it's the same. So so then okay, well, yeah, I'm slightly messed up here between rectangular and square matrices. But so let me just say that conclusion is correct. Okay, all right. I won't pursue that totally because I'm going to do something similar here. Okay, now, here, back to our least squares problem. This is a very, very basic problem and constantly being solved. Okay, and what are the ways to solve it? Way one is head-on. Just solve the normal equations. Way two is take your matrix and orthogonalize those columns. Make it into a Q. And then you got an easy problem. So can I follow through on that? Because that's like a decision that people are still arguing about. What's the best way? Do you tackle it head on, or do you first orthogonalize? And let me say, orthogonalize the columns of A. And now I have to say what that does. That's this famous QR. This is this Gram-Schmidt process, which my linear algebra lectures would have described, but I'm going to recall it here. So I'm going to take my A, and I'm going to produce out of it a Q, and there's going to have to be some matrix R that does the job. That does the job. So the columns of A were not orthogonal. The columns of Q are orthogonal, and there's an invertible matrix R that connects them. Okay. So this is what Gram-Schmidt achieves. And I'll come back to that. What I want to do is use it. Suppose I've orthogonalized the columns of A to get Q, and the R has done it. This is m by n. This is m by n, and this is n by n, nice and square and invertible and everything. In fact, triangular. R is a nice matrix. We've taken a not nice matrix, and we've factored it into a nice rectangular matrix and a very nice square matrix. But it costs something to do that. We had to, I'm going to be very practical here. Because I'm asking, what's the best way to solve this fundamental problem? Should we tackle it this way? And what would be the cost there? Or should we tackle it this way? All right, now if we tackle it this way, what will we get? So now I'm minimizing. Yeah, so what does it mean? What if A is QR, what's my answer here? Let's see. I'm minimizing AX minus B, but that's QR X minus B. And now, again, I can multiply by Q transpose, and I'm minimizing, I get Rx minus Q transpose B. And now I look for the best X, but R is invertible. So the best X is, let me just put it here, is R inverse Q transpose B. That's another way to do estimation. Another way to do estimation. And I guess this is way 2, and this is way 1. And the choice between those two ways is sort of quite fundamental. It comes up in Kalman filters every time, because Kalman filters are so many filters are doing least squares. And how's a way to describe that choice? Maybe you've heard of it in this filter connection. Here we're basically working with A squared. Somehow, A transpose A is the matrix version of A squared. Things are being squared. Here we aren't. Here we didn't work with A transpose A. We only stayed with A. So this is like the square root filter. Have you heard that expression in connection with filtering? Because it was like a bombshell in the world of Kalman filters. the suggestion of a square root filter. And why was it a bombshell? Because when I square stuff, I can mess up the condition number. I can mess up the stability. So these square root filters became very important because they're more stable. And condition number is, I'll come to in the second lecture this afternoon as a measure of stability. So, but here we're seeing, I mean, once we get to Kalman filters, we're going to get buried by so many important ideas. I thought maybe to see it in this simple case, simple being the cleanest possible case of a linear system, no solution. One option is go to A transpose A. Second option is orthogonalize the columns, and then you have, so this is triangular. No work is involved in that. No work. That's a simple matrix multiplication. That's really fast. Why wouldn't you just do number 2 every time? Yeah, you're really on the ball. That's it. You'd have to, because you can't do it until you've done this step. So the question is, what costs more? To do this step, and then you had triangular matrix, transpose. I mean, the solution of the system was no work. The work is in there. Where here was we have a linear system to solve. And so it's a regrettable fact. It's a pretty close race, but this one is faster, and this one is safer. So it depends. If you're risk averse, you do that one. If you figure, let's just get the answer here, this one. And maybe I could. I noticed in this an important Bible in this subject is the book by Golub and Van Loan. Do you? Let me just copy down some numbers from their book. I feel it's first useful to mention who are some of the leaders in this field. Gene Golub is certainly one. And Charlie Van Loan probably wrote most of the book. And he's at Cornell, and Golub is at Stanford. And it's now in its second edition. It just happened that at home I had this first edition, so I've brought that today to tell you the costs of the different ways that you could solve these squares. Okay. So this book is called Matrix Computations. It's pretty dense, but it gives the basic algorithms for numerical linear algebra. So it's kind of become the Bible in this subject. Okay. Golub is especially associated with the SVD, which is my next lecture. So yeah, actually his license plate is Dr. SVD, California plate. And I think he's quite proud of it, of course. But he's a good guy, a pretty good guy. He's okay. So I was going to write down the table of, okay, how many flops? So a flop is a floating point operation. And, well, either for solving a square system, yeah, I don't know if I've got all this is n by n. And do you know how many operations it takes to solve? It's symmetric, which will cut the operation count in half. How many operations to solve an n by n symmetric system? Anybody know? It goes up like n cubed, And then now we have to get to what number multiplies that n cubed? Because all these ways are going to turn out to be n cubed ways. And so the coefficient is what tells us whether one wins or another. And let's see, it's for a normal n by n matrix, it would be 1/3 n cubed multiplies and 1/3 n cubed adds. So 2/3 n cubed. But for a symmetric matrix, half of the work is not necessary. We don't have to worry about above the diagonal if we follow below the diagonal. So this method takes one, well, I was going to write it over here. This method, elimination, takes 1/3 of n cubed flops. Okay. And then there are other ways, but let me mention Gram-Schmidt, which is A equal QR, that idea. By the Gram-Schmidt method, well, it turned out to be n cubed. And using the SVD, is worse. In this case, the SVD is more. Still n cubed, but higher. There are other possibilities I won't list. People just spend a lot of time thinking, what's the efficient way to do these things? So there we see it in this choice of taking squaring or square root one in that simple context. And one of the things I hope to learn, maybe in conversation, is in filtering, have the square root filters triumphed? I don't know what the standard software is in that world. In this world, this simpler world, the standard, most people just go with that one because it's so simple and it's faster. Okay, so that's some comment about least squares and this A equal QR from Gram-Schmidt. Let's see, I had one more topic that I didn't want to miss out on. So so I'm going down the list here. I've spoken about costs, and now I wanted to speak about the eigenvalue problem. And then I really should say more about QR, but let me say something about the eigenvalue problem. Because finding eigenvalues, let's take a symmetric matrix. So A equal A transpose. Find the eigenvalues. Okay, that's one of the fundamental computing jobs, and it's not at all clear how to do it. I've mentioned when we spoke about when we introduced eigenvalues, that you would never want to use the determinant of A minus lambda I, figure out that polynomial and find its roots. Yeah, I mean, the roots of polynomials are quite difficult to find. Actually, I had a case in an event of that kind a week ago. We were using MATLAB, which of course computes to 16 digits. And forgive me if I mentioned this before, just say it again. We had a polynomial of degree 6, and we knew that 4 roots were at 1, or at minus 1. We knew we knew that our polynomial had 4 roots at minus 1. And the other 2 roots were real. So we knew what it was, and we'll actually see that polynomial in the wavelet lectures. And so we gave it to MATLAB, the roots command to find the roots. And I was disappointed. Actually, I was speaking to Cleve Moley yesterday, but I didn't mention this, that it found imaginary roots, complex roots, with quite a significant imaginary part. In other words, so I'll come back to this, but here is the complex plane. Yeah, I may have mentioned this. Here's the complex plane. Our polynomial had 4 roots here at -1, and what MATLAB produced were 4 roots in a little circle around -1 and partly complex. Okay, so all that's just to say, do not, if you can avoid it, don't get polynomials of high degree and look for their roots. Got to find a better way. Okay. Got to find a better way. So what's a better way? Well, here's this QR method. So somehow out of this is all numerical linear algebra in my lifetime, and maybe some of yours. Like when we were doing, well, I wasn't doing calculations in World War II, but when calculations were being done in World War II, there was no good way to find the eigenvalues of a matrix, even of order 20, which MATLAB will now just do in an instant. Because people thought, well, we take that polynomial of degree 20, find its roots, and it was ridiculous. Okay, so out of that need to find eigenvalues, gradually emerged something called the QR method. So here's the QR method in a nutshell. You orthogonalize. You orthogonalize. So you write, you factor A into QR. And then the next step of the method is you form RQ. You reverse the order of those two factors. And how is that matrix related to that one? So let me give this name, this matrix a name A2. Say this is A1. QR is our starting matrix. Okay, so you form this matrix, and this is A2. And how is it related to A1? Can you see what we've done? We've sort of rotated. So if I started with A1, which was the QR, what have I done to get RQ? Well, I guess I've multiplied by maybe a Q inverse, which is a Q transpose on one side, and by a Q on the other. Is that right? If I had QR and I multiplied by Q inverse on the left and Q on the right, then that gave me RQ. Okay. That's one step. That doesn't get you too far, but and the cost was, well, we've just seen what the cost is. Now we've got A2. Okay. Now we factor A2, the new guy, into QR. So that'll be a different QR. Oh, I've got to put ones on these things. So these were the ones. Ones were the subscripts all along there. Okay. Now take A2, and factor it into the normal, this factorization that I keep referring to. It's the Gram-Schmidt idea. We could create the algorithm that does it, and here it is in matrix language. We factor it like that. Now, what's the next step? You're going to now you can carry it on from here. What will be A3? Reverse the R and the Q. Put the R and the Q in the opposite order, and that will be A3. And again, that's the same as Q2 inverse A2 Q2, right? When we put the Q on the other side, we've multiplied by Q from the right and by Q inverse from the left. Okay, now first of all, what's this got to do with eigenvalues? And second, is it getting us anywhere? All right, first question, what does it have to do with eigenvalues? Well, my claim is that the eigenvalues aren't changing. that A2 and A3 and A4 and the whole sequence of numbers, of matrices, has the same eigenvalues as the original. So that's point one. So that, I'm speaking now of left orthogonality for the moment and talking about this famous method for finding eigenvalues. Can you tell me why A1 and A2 have the same eigenvalues? That's a very important point. And why is?
I think if a vector is, we have a vector that's being, say, stretched along the line.
Oh, right. Let's take.
Rotate. First you're rotating.
Right. Right.
The vector's being stretched along that line. Now you rotate back.
Rotate. Right. That's right.
So you're not.
Exactly. We had a vector, the original A, which I guess we're now calling A1, had a vector X, right, that was being stretched. Good. Now, what about A? Let's see. What if I multiply, do this, as you said, I should just now rotate everything. So shall I rotate it by Q1 inverse? So I'll rotate everything by Q1 inverse. And now my X, let me call that Q1Y. Let me just change, again, I'm rotating. So let this X be Q1Y. So this X is Q1Y. I'm doing a proof by erasure here, which is easy on the blackboard. What have I got? Well, Q1 inverse Q1 is identity. So I've learned that Q1 inverse A1 Q1 Y, this is the eigenvector, but the eigenvalue is the same. You said it, and I probably didn't do it as clearly as you said it. That if I have an eigenvector of A1, it's a vector that's just stretched. When I rotate, it rotates into a vector that's also just stretched. That's the key idea. So the eigenvalues don't change. And remember from the very beginning, the matrices aren't getting any wilder. And in fact, they're getting better. That's somewhat of a mystery, but it's true that this sequence of matrices gets more and more diagonal. The eigenvalues in about 4 or 5 steps, or at least one of the eigenvalues will show up on the main diagonal with just little off-diagonal entries, so it's slightly wrong. I can't get it exactly right, but I can get it as accurately as possible. So that's this famous QR method. You see why it's named QR, because at every step we're doing a QR factorization. We're doing a matrix multiplication to get the new matrix. We're doing QR on that, a matrix multiplication to get A3, and so forth. And quite efficiently, the eigenvalues come out. That second part I haven't explained here. That why this thing should get closer and closer to the eigenvalues. We could test it if we wanted on a particular, on a 2x2 model to see why that would happen. If we, maybe I'll just, so there's a discussion of this in the textbook. So some of this lecture quite a bit of this lecture is discussed in Chapter 5 of the Applied Math book, the blue book. So I've covered the topics that I promised in what I feel a slightly noisy manner. Maybe less smooth than I wish. Can I recap? The virtues of orthogonal matrices are lengths don't change, angles don't change, eigenvalues don't change, and therefore this question arises: if we have a bunch of vectors in A, should we straighten them out to be orthogonal by a matrix R? And that process, that's one of the most important factorizations in linear algebra. So I might say one more word about that at the beginning of the next lecture, this A equal QR, because I popped it up there without saying where it came from. But the main point is that then least squares, projections, all the operations of linear algebra become so simple when we have orthogonal matrices. So I hope that's okay as a justification for concentrating on these orthonormal guys. I could take a question or two, but yes, thanks, and I'll repeat.
Before when you're comparing the computational cost.
Yes, comparing the cost.
With safety. Are you going to specify safety at some point?
I will. But actually, so the question was, should I introduce what safety means? Well, how could we estimate how can we estimate numerical errors? Which problems are ill-conditioned? Which problems are well-conditioned? And yeah, so maybe the next lecture is the perfect one to pin down that idea of conditioning, condition numbers. Okay, so let's take our break. Another question. Yeah.
How do you know when to stop there? How do you know
Oh, how do you know when to stop? Well, what you see in this QR method, so the question is when to stop. What you'll see in this QR method is it happens first down here. We get a tiny little number, which of course I'm going to call epsilon, meaning tiny. It shows up there, and we'll stay symmetric. So we'll have still significant numbers beside the diagonal, but the first ones to get small are that. So when that's below some tolerance, then this is an eigenvalue. Because if that was a 0, that really would be an eigenvalue. And then you could, if you liked, knock that part of the matrix out, keep going, deflation that's called. Another 3 or 4, this guy will have been getting smaller. Another 3 or 4 steps, it'll be an epsilon, and you'll see sitting there the next eigenvalue. It's quite like wonderful. And actually, it has been the winning method for eigenvalues until somebody came up with an alternative just a couple of years ago, which I won't attempt to describe, time already having run out. But I can say roughly what happened. This new algorithm is called divide and conquer. So this time, there's so much ingenuity in this stuff. So let's say we have one of our tridiagonal matrices, which is actually the good way. The first thing to do in all these methods is to get these zeros that I spoke about at the beginning of the lecture. We can get zeros here, no problem. What we can't do is make those zeros, because if we could do that, then the eigenvalues would be sitting there. We can't do that except by some idea. So this QR idea gets zeros like gradually, but pretty quickly. Here's this divide and conquer idea. The divide and conquer idea is deal with that matrix and this one. Suppose we knew the eigenvalues of this half-size guy. That's going to be faster. And the eigenvalues of this half-size guy. Then well, we haven't got, those aren't eigenvalues of the whole thing. Why not? Because of this little rank 2 matrix that's connecting them. So there's an iteration, of course. to gradually work, connect. So you see the idea of, you see why the name divide and conquer. You divide the matrix into half, you work on this half, and then make the adjustment, which of course is going to be the serious part, to deal with that. And then of course, how do you do this one? Yep, divide and conquer again. Right, we've got the idea, except for knowing what to do with this. And it seems such a natural idea. It's amazing that it didn't come until pretty recently. Okay, you're seeing like numerical linear algebra in commotion here. And the second lecture today will be the other great factorization, some people say the greatest, the singular value decomposition. Jean Golub would say the greatest, yes. Okay, thanks.